Right. Hello, everyone. Okay, please listen to this lecture and write down whatever you need to, okay, in your sound notes as well. Yeah, I hope to keep this to within 30 minutes. Okay, so without further ado, anyway, you can speed up this video anytime you want. All right, so let's go into what sound is. Okay, now if you recall about Slinky toy that we use in class, right? When it's being pushed and pulled in, let's say a horizontal direction, okay, like this. Let's say a wave generator pushing the slinky in a forward motion, right? As it push it forward, you will notice that uh, it produces this dark region, right? Where the coil starts to be compressed at a region and it will move across all the way to the other end of the spring. Now, since the particles, okay, on this coil is moving in a horizontal direction, right? When the wave generator pushes it forward, the particles will move forward, okay? And then when it pulls back, right? When the wave generator pulls back, it will pull the particles backwards again, right? So this forward and backwards motion coupled with how the wave direction is, right? This series of compression traveling across to the other end. So since they have a parallel direction, we also call this a longitudinal wave. Okay, please take note, you need to know how to spell it accurately. So when it creates this region of compression, right? And areas whereby it's being stretched because this spring it has a fixed length, right? So if some parts are being compressed, then definitely you have some parts whereby the spring looks very sparse, right? Looks very spaced apart. So these regions are what we call rarefactions. And you will notice that there's a certain pattern to it. Okay. If you have a region of compression, right, next to it, because of the length of the spring, right, it's fixed, right? Uh, you will have this region whereby it's very sparse, very spaced out. Okay, we call that a rarefaction, and then followed by compression again. Okay, so just to give you a visual of how the sound travels, right? Imagine this is the tuning fork, right? When I hit it, it will vibrate. So this vibration, mimics the forward and backward movement of the wave generator in the previous slide. So when it pushes, right, uh, the air molecules will be pushed forward, and in turn, it will push the other air molecules as well, right? And you will see something moving across. So this moving across is really the energy transfer or the transfer of energy, and each of the particles are actually just moving, parallel to the wave direction, but they don't actually travel with the wave. All right, so you can see again this series of compression just moving across, uh, this medium. So now when it comes to describing, because the question might ask you how is this wave generated, or how does sound travel from one point to the other, right? What we need to mention, okay, first of all, mention there is a longitudinal wave, right? Caused by whatever the vibrating source may be. So it may be a tuning fork based on the question. It may be a slinky wave coil. Oh, sorry, that's the medium. Uh, I don't know, it might be your hand pushing forward and backwards on the slinky coil. Okay, so this part you need to contextualize. Okay, and create alternate regions of compression and rarefaction. And lastly, mention about, the key point about a wave, which is transferring energy. Okay, so you just need to write out two key ideas in your blank. So again, just to explain, right? In the absence of sound wave, the air is uniformly dense, right? Every part it has a uniform density, and they are evenly distributed, right? Of course, not in a very neat, super neat way, right? But we can always mark out like a mean position, right? These are the mean resting position of the column of air molecules. Okay, so what happens is that when we turn it on, then you will see that, hey, this column of air molecules have shifted from their original position, right? So this is the mean average position of all the air molecules in that column now. So again, right, once you see them compressing at certain point, okay, these are what we call the compressions. Okay, then also have areas whereby they are very sparse. Okay, then these are the rarefactions, compression again. Now we're gonna draw this or relate this into a graph, right? Again, if you recall, when we looked at all the particles in a wave, like we take a snapshot, right? If we take a snapshot of all the particles in a wave, what kind of graph can we draw? Okay, we can draw the displacement distance graph. So between between uh the original state, okay, whereby there's no disturbance in the medium, and then versus, when we added on uh when there's a vibrating source, right? We can compare how, at each column of the air molecules, how it has changed in that particular instance. So for example, right, if you look at this column here, compare compare it to, when there's a vibrating source, it has remained roughly the same position, right? And then when we look at the middle part over here, this is the original position. And then afterwards, this part, there's also, at the same exact position, but just that it has changed in terms of the molecules that are around it. So now we have a compression, right, whereby two sides of the air molecules are at this instance whereby both columns are squeezing this middle part. I mean, that's why it's called compression, right? It's being squeezed from both sides. Okay, and then this part again, whereby no change compared to the previous original state, but the molecules from both sides of it has moved away from it. Okay, and then this one again. So, if we were to draw out how the displacement has changed for, let's say, this part, these four parts, okay, compared to, its original state, is there any change in the displacement? Right? There wouldn't be any change in displacement. So if there's no change, naturally we'll put our coordinates, right? Falling on the axis itself because there's no change in the displacement. But again, right? But now thing to notice is between each of the rarefaction and the compression, right? This is where things will get very interesting between, let's say, rarefaction and the compression. Okay, so rarefaction, particles are trying to get away from it, right? Particles are getting away from it. Compression, right? Columns that are very near it, uh, they are squeezing the region of compression. So in that case, let's take a direction. Let's say the rightwards direction is positive, right? Displacement to the right is positive. So that tells us that, hey, actually all the molecules here, right, will have a positive displacement. Okay, so if I were to compare, right, this was the second column compared to this column, right? Was also this is the second column as well. So if I compare the change in the displacement for each of the column, then I'll notice that, hey, actually is slowly increasing in a sinusoidal manner, right? All of this column of air molecules will have a positive displacement, just that the positive displacement will be different at different juncture. Okay, so you will have a positive, like your sine graph. Right. On the other hand, let me use another color. So on another hand, let me erase away. Okay. On the other hand, uh, let's say from the compression and the rarefaction. So let's say the right side of the compression, all the particles are squeezing towards it, right? So they will travel a negative displacement direction. Same thing for the left side of the rarefaction is also traveling away from that region, right? That's why there's a rarefaction now, because particles are trying to get away from it. So in that case, it will have a negative displacement in the graph. Okay, and again, it will follow the sinusoidal uh, curve. So if we repeat this argument, right, you will notice that, hey, again, it falls into place like your sine graph again. Okay, because at different region, the particles are behaving in a specific manner. Okay, let me just add it on. Okay, so if we want to look at the maximum displacement at any point, right, it will actually be the middle of your rarefaction and compression, the middle, right? Because compared to its original state of the particles, it will have the greatest change in the displacement. So it might be positive, it might be negative displacement. So no, when we talk about displacement distance graph, okay, take note, we can always read off the wavelength, but never the period, right? Because again, there's no time scale in this. With just a snapshot, I cannot tell how long it travels. Okay, so in that case, uh, when it comes to reading off the wavelength in a displacement distance graph, right? The common trick here is you can read from crest to the next crest, right? Or trough to trough again, in the previous chapter, right? But really, the wavelength is basically just the distance between any two, sorry, just the distance between, right, crest to the next crest, right? Or just any 2 points that are in phase. So in that case, I can also read off from, let's say, the resting position here to the next point that is in phase to that. Okay. or rather, one complete pattern lah, right? These 2 points, they are in phase. So in that case, this gives me the wavelength, right, of this particular sound wave. So again, if we were to read off, let's say, or rather we transfer this knowledge whereby from uh, 2 points, they are in phase here, we relate it to the diagram, right? Where exactly does all this equilibrium position lie on in the diagram above, right? You will realize that actually is the rarefactions. So actually between two rarefactions, you can also read off the wavelength of a graph. So if you can read off from two rarefactions, that means you can also read off from two compression. Right, make sense? So in that case, how do we read off the wavelength from a sound wave? Okay, basically instead of crest to crest, right? Because again, crest to crest only applies to in the idea of a transverse wave, right? The highest point of a wave. But just because there's a hump here doesn't mean that it's necessarily a crest, just a maximum displacement. So in that case, um, we could, right, tell the wavelength of a sound wave as the distance between two successive compression or rarefactions. Okay, that will give you the answer or to find the wavelength of this sound wave. So if let's say from rarefaction to rarefaction, right? This is a wavelength denoted by lambda, or you can read off from compression to compression. So I draw it here. Yeah. You could also tell from here, right? These 2 points are in phase. So this gives you the lambda as well. It gives you the same value. Now, there's another term for sound wave, right? Often it's also named as a pressure wave, right? Why a pressure wave? So if you think about it, right, when there's the region of compression and rarefaction. Let's say this region compression is being squeezed on both sides. So how will the pressure be like in that region? Right, it has to be of a maximum pressure, right? So if let's say I want to plot a graph whereby it's a pressure versus a distance graph, right? This compression would result in a maximum pressure in the region, right? Therefore, this in a positive direction because a lot of pressure on it, right? And then how about the area whereby there's the rarefaction? So particles are getting away from it. So the pressure that, at the rarefaction, all the air molecules over there, they will feel like, oh, there's no one squeezing me anymore, right? So the pressure over there will be a minimum. So if I were to plot out all the points again, right, the compression as the maximum pressure, rarefaction minimum pressure, right, your compression, and minimum pressure, rarefactions, right? Once I draw out the graph, I can also tell the wavelength very easily because, it will behave almost like your transverse wave, right? Your graph from transverse wave, where you can read from crest to crest, right? That's also another way how we can represent sound wave. Now, take note, over here, right, on the axis, this is not zero pressure, right? Instead, they are using this acronym PATM, which stands for atmospheric pressure, right? Or rather, the pressure at that particular point, if there was no disturbance in the air medium, right? Basically, if there's no sound wave, then all the pressure will be uniform, right, along this axis. So it's not that it's zero, it's just that it has a certain value and it will be like a constant value. But because of the disturbance, so we can use this as a reference to see, how much has our pressure increase or decrease. So from here, I can also tell from pressure distance graph, I can tell what the wavelength of a sound wave is, right? Looking at from one hum to the other. 2 points that are in phase. Okay, now, so sound relies on the passing of motion from a group of particles to another group, right? To its adjacent group through collision. So that means that sound cannot travel through a vacuum whereby there's nothing, right? There's no matter for the collision to happen if if the medium isn't pressure present, then there's no way that sound wave can even be generated. So for example, if let's say I have a bell, right? If we were to remove all the air, then the sound of the bell will become softer and softer. Eventually, will just disappear altogether. Even though you will see the striker, right, hitting the bell constantly. So it will hit. But if let's say we suck out all the air, right, through a pump, then eventually you will not hear any sound coming from the bell anymore because there's no more collision of these particles. Okay, so that okay, I will check this video. No, I think I have to play this video. Okay, let's take a look. Why? You can, think about this yourself. Again, if the mechanism of sound wave is through the collision of particles at higher or lower temperature, how would that affect the collision? Right? At different air pressure, how will it affect the collision? Okay, so I'm gonna pause here, right? We can see a trend in how speed of sound will change in different state of medium. Okay, so just very simple, right? Speed of sound, how it changes in different medium. In solid will be definitely the fastest. Why? Because of the arrangements of the particles in solid, right? Very closely spaced, sorry. Very closely packed, yes. Very closely packed. So therefore the collisions can happen at a faster rate, right? Compared to liquid, compared to gas. So let's look at one example. Now the vertical lines shows a uniform mean spacing of the air particles without a sound wave, right? The original state. Then the next diagram shows the varying spaces when a sound wave is introduced. So label the regions of rarefactions are. Oh no, by the way, please, you can pause this video if you like to try yourself first, right? After you tried it, then you can continue playing the video. I think that will be more useful for you if you can try it on your own first. So label the regions of rarefactions with R. So uh, I think quite obvious, right? You can see all these regions here whereby, the particles are very close to one another. So that represents what? A region, right, of compression, right? So if between compression and compression, right, the particles that are very spaced apart, right, will happen in the middle. So therefore, we can say that the middle of these two compression will be, let me see, 1, 2, 3, 4. So you can count the number of lines and then to determine where the middle line will be. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So between, let's say, this and this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So maybe over here, this is the rarefaction, right? And then between the other compression, uh, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5. This one. Okay. So these are the rarefactions in the sound wave. Again, the middle of the two compression. Then B, how does the air pressure at R compare to the atmospheric pressure? Uh, well, it's quite obvious, right? The air pressure at R, if the particles are going away from it, pressure at R is lower than the atmospheric pressure. Okay, then part C, in the figure below, use the axis provided, draw the displacement distance graph corresponding to the sound wave. Okay, so remember, just now we said the rarefactions, compressions, right? They will all be, the particles will be at their equilibrium position. So it's either uh, the particles around them are squeezing them or getting away from them. So the particles itself at the rarefaction and compression, they will all be at the displacement. All right, so again, we use the method just now. Now we have to determine, right, whether, let's say, different parts of the graph, is it upwards? Is it a positive displacement or is it a negative displacement? Okay, this is when we have to determine, right? Let's say for this part, the compression. No, it's compression. So the particles on the right hand side, how are they moving? Right? So we know that it's squeezing it, so it must be going away, or sorry, traveling in the negative displacement direction. If let's say take right as positive, So in that case, I know that, oh, the particles on the right-hand side of compression is gonna be negative. Same thing. On the left-hand side of the rarefaction is also going away. So I know it has to be a negative displacement direction. So in that case, once I know that, actually I can continue drawing the graph already. Okay, pardon me, because I'm drawing on an iPad, so it's not very smooth. But you should try and draw yours as smooth as possible while ensuring that, okay, both side of your maximum displacement, no, this one too high. Okay, while ensuring that the maximum displacement on the positive and the negative region, they are the same. So what you can do is actually use a ruler, draw uh, all these dotted lines to, in a way, provide guidance for how you draw your curve. So, continue. Mhm. Amen. Sorry, it's not ugly. Okay, yes. So this is the displacement distance graph. Next one, how sound wave travel through the air from the speaker to point A, and then explain why sound cannot be heard. Yeah, I think it's quite simple. You can just refer to uh the front part, right? I gave you the, in a way, a template on how you can answer sound question. So I'm not gonna go through this. It's quite standard. Okay, as long as this part you mention longitudinal wave. Okay, at the end lah, when you mention, oh, sound is a longitudinal wave, right? You mention how the sound is generated, right, through the speaker when it pushes the air uh forward and backwards repeatedly. Right? As long as you have this forward and backward uh motion, oh sorry, no, yeah. As long as you describe this motion, and having an idea that it does it repeatedly, then you'll be fine. Okay, explain why sound cannot be heard. First, need medium to for the collisions to happen. Okay. All right. Next one, label the compressions and rarefactions in the box. Okay, so I think it's quite simple. Compression, rarefaction, compression, rarefaction, compression. Oh no, what's part B? Part B is calculate the wavelength. So okay, given that this is 10 cm, so I know that the wavelength has to be between 2 points of the same phase, right? So either compression to compression, right? Rarefaction to rarefaction. So in that case, I'm gonna measure it like this. 10 cm is, 2 times the distance of compression to the next compression. Okay, or we use the word successive. In that case, right, in that case, very simple. Wavelength is 5 cm. Okay, C. State how the speed of sound will change. Speed of sound will increase in water. Right, so this is the first part.